Welcome to The Explainer. So, have you ever actually stopped to think about what's driving the weather outside your window literally right now? I mean, the Earth's atmosphere isn't just, empty space. It's actually a massive, invisible heat engine. Every single breeze you feel, every cloud you see, every crazy storm, it's all just this engine relentlessly trying to balance out its temperature across the entire globe. Today, we're going to pop the hood and look right inside this incredible planetary machine.
Here's our roadmap for today. First, the engine of weather. Second, global wind circulation. Third, clashing air masses. And finally, nature's fury. Let's get right into it.
All right, part 1. The engine of weather, setting the air in motion.
To really grasp how this global weather engine gets its ignition, we kind of have to start with the microscopic stuff. We rarely think about the sheer weight of the sky, right? But atmospheric pressure is quite literally the weight of a massive column of air resting right on your shoulders at this very moment. Down here at sea level, that pressure averages around 1,013.2 millibars. But as you go up, the air gets thinner really fast. In the lower atmosphere, that pressure drops by roughly 1 millibar for every 10 meters you climb. And here's the kicker. These pressure differences, whether they're vertical or spread horizontally across the Earth, well, they are the absolute primary cause of all air motion.
So air doesn't just decide to get up and move on its own. It's actually being pushed and pulled by 3 main forces. First up is the pressure gradient force. You can think of this as the main driver. Air inherently wants to rush from areas of high pressure over to low pressure, just trying to fill a void. Second is the frictional force. The Earth isn't a perfectly smooth marble. Trees, mountains, buildings, basically the Earth's giant speed bumps drag on the wind and slow it down, mostly in those lower 1 to 3 kilometers of the atmosphere. And then, there's a third, much stranger force at play.
Which actually brings us to a huge question. If the pressure gradient is pushing air directly from high to low, why don't winds just blow in a straight line? Seriously, why do weather systems always look like giant swirling spirals on satellite maps instead of straight arrows?
Well, the answer is the Coriolis force. Because our Earth is constantly spinning on its axis, it throws a literal curveball at the wind. It deflects wind to the right in the northern hemisphere and to the left in the southern hemisphere. And a super important rule of our weather engine is that this deflection is directly tied to your latitude, meaning it's at its absolute maximum at the poles and totally 100% absent at the equator. This one little quirk of physics is the exact reason winds end up swirling around pressure centers instead of just shooting straight in. Moving on to part 2. Global wind circulation, the planetary machine. Okay, so we've looked at the microforces. Now, let's zoom way out to the entire planet. The sun is just beating down intensely at the equator, specifically at this low-pressure zone called the Intertropical Convergence Zone, or ITCZ. This intense heat causes warm, moist air to shoot up, sometimes 14 kilometers right into the sky. As it rises, it spreads towards the poles, cools off, sinks back down around 30 degrees latitude, and then flows right back to the equator. This creates these massive, continuously circulating convection loops that we call cells. And this whole setup is exactly how our planet transfers all that tropical heat toward the freezing poles. Now, we can actually break these massive loops down into 3 distinct gears turning across the globe. First, you've got the Hadley cell right in the tropics, driven directly by the sun's intense heat making that air rise. On the total opposite ends, you have the polar cells, where freezing, super dense air sinks and pushes toward the mid-latitudes. And then, sandwiched right between them is the Ferrel cell. This mid-latitude zone is a total battleground. It's defined by sinking cold air from the poles just slamming into rising warm air from the subtropics. Because it's wedged in the middle like that, it's where a ton of our most chaotic, unpredictable weather happens.
But hey, the atmosphere absolutely is not working alone here. The oceans are completely tangled up in this circulation. A perfect example of this is the ENSO effect, El Niño in the Southern Oscillation. When warm water in the Central Pacific slowly drifts eastward towards South America, it literally changes the atmospheric pressure over vast stretches of the ocean. This massive ocean-atmosphere handshake alters the whole planetary machine. We're talking domino effects triggering global weather extremes, crazy heavy rain on the usually dry coast of South America, brutal droughts in Australia, and even terrible floods over in China. It just goes to show how insanely interconnected this whole engine really is.
All right, part 3. Clashing air masses, when fronts collide.
So let's see what actually happens when the massive blocks of air created by those global cells crash into one another. You see, when air just sits over a vast region, like a huge ocean or a massive snowy continent, it takes on the temperature and moisture of that specific area. it becomes this distinct air mass. But when two different air masses meet, they do not mix easily. The boundary line where they hit is called a front. If a cold air mass aggressively bullies its way into warm air, it violently forces that lighter warm air straight up, creating a cold front with really steep gradients. But if warm air is moving in, it kind of gently glides up and over the top of the heavier cold air, which gives us a warm front. Either way, these collisions force air upward, and that upward motion is the exact recipe you need to form clouds and get precipitation.
And you know, this doesn't just happen on some massive planetary scale. Your local geography plays a huge role too. Think about going to the beach. During the day, the sand heats up way faster than the ocean water. So the hot air over the land rises, creates a pocket of low pressure, and boom, cooler, higher pressure air from the sea rushes in to fill the gap. That's your nice, refreshing sea breeze. But at night, the whole process perfectly reverses. The land cools down much faster than the water, creating higher pressure over the land, and the breeze turns around and blows right back out to sea. It's the exact same planetary engine at work, just playing out right in your backyard.
Which brings us to Part 4, Nature's Fury, the climax of circulation. Now we're entering the climax of the explainer, Earth's most extreme, highly visible weather events. And I really want to pose this question. What actually fuels the world's most violent storms? I mean, we've talked about pressure and fronts, but how do those ingredients combine to create massive, devastating cyclones? When we compare the big storm systems, a pretty stark difference emerges. Extratropical cyclones happen in those mid-latitudes, and they're driven entirely by those clashing temperature fronts we just talked about. They cover huge areas and generally sweep from west to east. But tropical cyclones, which you probably know as hurricanes or typhoons, are a completely different beast. Get this, they have zero fronts, none. They only form over warm oceans where the surface temperature is above 27 degrees Celsius because they are purely heat engines. They suck up massive amounts of moisture and latent heat from that warm ocean water to build these towering cloud formations. And it's exactly why the moment they make landfall and lose that warm water supply, they start to immediately die out.
If you look deep inside the anatomy of one of these monsters, right smack in the center is the eye. It's this super eerie, calm region with slowly sinking air. But immediately surrounding that calm is the eye wall, and this is where warm, moist air spirals upward with just unbelievable violence. We're talking winds in the eye wall reaching up to 250 kilometers per hour, dumping absolute torrents of rain. And of course, all that intense, terrifying rotation is driven by our old friend from earlier, the Coriolis force. Now, on a smaller but still highly destructive scale, we've got severe local storms, your thunderstorms and tornadoes. Basically, on really hot, moist days, you get these intense updrafts of warm air that build massive cumulonimbus clouds. When the tops of those clouds reach sub-zero altitudes, that's when you start seeing hail and severe downdrafts. In the most extreme cases, this violently twisting air can actually spawn a descending, spiraling funnel of incredibly low pressure, a tornado. They're highly localized and usually short-lived, but they essentially act like a giant, wildly destructive atmospheric vacuum cleaner. I want to leave you with this final, really profound thought straight from our source material. These violent storms are the manifestation of the atmosphere's adjustments to varying energy distribution. Think about that. Whether it's a gentle sea breeze on your local coast, the massive global gears of the Hadley cells, or the devastating 250 km/h winds of a hurricane's eye wall, it's all completely connected. The heat and potential energy from the sun are just being converted into the kinetic energy of the wind. It's just Earth's restless, fascinating engine, constantly churning, desperately trying to find its balance. But as our oceans continue to heat up and we pump even more energy into this closed system, you really have to wonder, how much more violent will the atmosphere's adjustments become in the years ahead?